Okay, so today we're going to start on Newton's method. Okay, and that's where you use the tangent lines to approximate y-intercepts. I mean, not y-intercept, x-intercepts, which is where y is equal to 0. Basically where it crosses the x-axis. All right, so if we kind of look at it graphically, okay, so if you remember, I'm just going to put a little reminder of the intermediate value theorem. Okay. Remember the first, it's continuous on an interval a to b. It's differentiable on the interval a to b. And if f of a and f of b have different signs, and it's continuous and differentiable, that means at some point a 0 exists. F of a and f of b have different signs, then some f of x equals 0 exists. Let me try to clean that up a little bit. Oops. Too many sheets. Let me move some of this paper. All right, so let's say if we have a particular graph that's continuous from a to b, let this be our a, and let's say somewhere down here is our b. So it's continuous from a to b. It's differentiable. There are no open spots or blank spaces or jump continuities. And let's say we have our f of a is positive and our f of b is negative. Okay, so let's say we want to find out exactly where this point C is, where it crosses the x-axis. Okay, so let's say that we pick some value x1. Okay, so we'll call this our x1. And we figure out our slope at x1. Okay, if we keep extending that tangent line, it will cross that x-axis. And we'll say it'll cross it at some x2. Okay, so now what if we pick that x2 on the graph and we find the tangent line of that point? Then that tangent line is going to keep going and going and going till it crosses at some point x3. And then we find the point on that graph where it gets closer, and then that goes, and then it gets closer and closer and closer. And eventually you'll put enough tangent lines up there to where you'll cross it right at C. Because if you notice, where you started your x1 and went to x2, your x3 is a little bit closer. If you did x4, it'll be a little bit closer than x2. So as it keeps getting closer and closer and closer and closer and closer, it's going to hone right in on that C value. All right, so any questions on that one? All right, so that's it graphically. So if we look at it, yes, as far as equations go. Okay, so let's say if we start with our good old reliable slope is equal to y minus y1 over x minus x1. And let's say if we let y equals f of x. Okay, so if we multiply both sides by x minus x1, you get y minus y1. Well, actually, you don't have to let y equal f of x because we'll show you, well, I'll show you why in a second. Equals the slope times x minus x1. Okay, so remember, we're looking for a value where your y is equal to 0. Uh-oh, we got y1. Okay, so remember your y is equal to 0, so that's why we really didn't need that y equals f of x. Okay, so now we're just going to solve for x. And also remember that that's just your f prime of x, your slope. Okay, so if we wrote that in, we have our, yeah, we can go ahead and do that. So, yeah, make that f1. There we go. So that's 0 equals y1 plus m times x minus x1. All right. Oh, that's right. We did already replace that with f prime of x. I don't know why I rewrote that. All right. So if we go ahead and distribute our f prime of x, we end up with, oh, here we go, f prime of x times x minus f prime of x times x of 1 plus our y of 1, we can make that f of x1 equals 0. Okay, then we just go ahead and subtract our f of x1. Actually, we can make that f prime of x times x of 1 minus f of x of 1. Okay, just divide both sides by f prime of x. Our x is equal to, I'll go ahead and rewrite it, f prime of x, x1 over f prime of x minus f of x1 over f prime of x. And it seems like I'm missing something. Nope, no, I'm not. Okay. All right, so x equals, these two cancel out. So you have x1 minus f of x1 all over f prime of x1. Okay. So what we're doing is we're using our first tangent line till it goes through our x-axis, and then we're going to use that to find our second. So really, this becomes x2 is equal to x1 minus f of x1 over f prime of x1, because we're now going to use that x2 and do the same thing over again. Oh.
Your third line up, is that a y, f prime of x, y1 or x1? I can't see at this angle.
Wait,
down,
this one?
Down two more.
This one?
To the right, yeah. Is that
This,
a y or an x?
This is x of 1.
Okay.
Yeah.
It's hard to see from this angle.
All right, no problem. All right, so here, repeat until you get closer to the value c, where f of c is equal to 0. Okay, so we just keep repeating that over and over and over and over again. And that will give us, oh, I'm just going to move this up a little bit. So we'll continue that. X sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. Okay, because you'll solve for x2 and use that for x3. And you'll solve for x3, use that for x4. And it keeps going back and forth. Yes?
Sorry, I don't mean to go all the way back, but I missed the transition where we went from, where did the y1 go and x sub 1 come from? Are those interchangeable? Is that what you're saying?
Oh, no, just y1. Because if you have your points y1, x1, all we did was replace y1 with f of x sub 1.
That's what I was asking.
Oh, yeah.
Interchangeable?
Yeah, because it's just y is equal to f of x, so just kind of switch them up. All right, and this is your formula for Newton's method.
In the third step, when you had the x multiplied by f prime of x minus f prime of x, all that, how did you get to the next step? Because
Which one? You talking about this step or one down?
one more down afterwards.
This one?
I understand that you would have to, it would be subtracting, right? You would have to subtract x f of x.
Mm-hmm. Yep, so all I did was here, I have f prime of x times x
Right.
minus f prime of x times x sub 1. So what I did here was just have it, oh, where is it?
So shouldn't it be?
Yep, so f prime x times f prime of x minus f prime of x times x sub 1 plus your y sub 1, which we turned into f of x sub 1.
Yep.
Okay, equals 0.
Okay.
Okay, so what I did was I subtracted f of x sub 1, which is right there.
Oh, you subtracted now.
Yep.
Okay.
Then I added that. So just to get the x by itself.
Oh, okay. X f of x.
Yep.
Is what we were trying to get for. Okay.
Yep. So then just divided by f prime, those two canceled out, which just left x sub 1.
Okay, I see.
All right. Okay. Anyone still writing the first page? Oh, okay. All right. So everybody else got it. All right. Let me bring that up a little bit. All right, so let's say, for example, say when I was about to use K, and I did that like 4 times today. When Newton's method is used to approximate the root of f of x equals x to the third minus 2x squared minus 3x minus 2 in the interval from 3 to 4, what is x sub 2 rounded to the nearest hundredths? Okay, and we're going to use x sub 0 equals 4, and we're going to round up for each iteration. well, up to the nearest iteration. That makes a difference. All right, so to solve this one, first thing you want to do is find f of x sub n and f prime of x sub n. And really, that's just changing every x to x sub n. Okay, so our f of x sub n is equal to x sub n cubed minus 2x sub n squared minus 3x sub n minus 2. And derivative is just the same as the derivative of a regular x. That's 3x sub n squared minus 4x sub n minus 3. Okay, so your second step, you're already given that x sub 0 is equal to 4. They gave that to you because you have to start somewhere. And we're going to use that to find x sub 1. So in other words, in our formula, that means we're going to make n equal 0. Okay? So if we made n equals 0, that would be x of 0 sub 1, so that gives you x1 equals x0 minus f of x0 over f prime of x0. Okay, so remember our f0 is 4. So that means that our x1 is going to equal 4 minus f of 4 over f prime of 4. Okay, so if we plug those in, I'll do it on a new line. It's going to get a little bit cramped. Our x1 is equal to 4 minus our f of 4 is 4 to the third minus 2 times 4 squared minus 3 times 4 minus 2 divided by 3 times 4 squared minus 4 times 4 minus 3. Oh, bring that up some. All right, so when you're done calculating all of that, you'll actually end up with an x1 that's rounded to 3.38. Remember, you have to round it on each step to the nearest hundredth. Okay, so that's our first one. They want us to go all the way to our second one. So that means we have to do that again, but everything will go up 1. So that'll be x2 equals x1 minus f of x1 over f prime of x1. And I should have enough room. Let me kind of separate that a little bit. Okay, so our third step. Now here we are given that our x1 is equal to 3.38. So now we have to find x2. So in other words, that means n is going to equal 1 in our formula. Okay, so if we make n equals 1, that gives us our x2 minus x1. Oh, equals x1 minus f of x1 over f prime of x1. So x2 equals x1 minus f of x1 over f prime of x1. Okay, so that means our x2 is going to equal our x1, which is 3.38, minus our f of x1, which is f of 3.38, over f prime of 3.38. Okay, so that means, move that over a little bit, our x2 is going to equal 3.38 minus our f of 3.38 is, wrong one. Is minus 3.38 to the third power minus 2 times 3.38 squared. Bring that over a little more. Minus 3 times 3.38 minus 2 all over 3 times 3.38 squared minus 4 times 3.38 minus 3. Make that first 3.38 a little bigger. Okay. By the time you plug all of that in, your x2 should equal 3.18. Uh-oh. All right, and that's where you'll stop. Now, if they ask you to go for x3, then you plug that in and you do that all over again. But for the most part, they usually just ask for the second iteration. Which doesn't seem fair. I remember my teacher making me go to the 6th. All right, so any questions on that one? All right, leave that up for a few seconds. All right. So I have another example I'm going to scan. It's pretty much the same thing over again. But I wanted to get started on antiderivatives. Okay. Which is just like the name says, it undoes all of the derivatives. Undoes. Antiderivative reverses the derivative. Okay. So let's say let's say we'll note this one. This one will be it's a little side note. Okay, so as a side note, if you notice, let's say f of x equals x to the third. Let's say if you have f of x equals x to the third minus 5. And let's say if you have f of x equals x to the third plus 85. Okay. All of them have the exact same derivative. f prime of x equals 3x squared. That's because those constants always disappear, no matter what it is. Okay? So if we reverse this, this will just become x to the third power plus some constant c. So you'll always add a plus c whenever you use the antiderivative, because it can always be a constant there, even if the constant is just 0. All right? Okay, so let's actually get to the formulas. Make sure I didn't skip anything we may need. Actually, let's go to the notation. For antiderivatives. Okay, so if you remember your differential, y is equal to f of x dx. Okay, and also if you remember, the antiderivatives will reverse derivatives. It's kind of like how division will reverse multiplication. So if you multiply something by 3, then divide it by 3, you just deleted it. All right? So antiderivatives use the integral sign, which is kind of like an overstretched S. Okay, so the antiderivative of the differential of y is equal to the antiderivative of f of x with respect to x. Okay, so we know the integral and differential cancel each other out. So that's y equals the integral of f of x dx plus c. No, not really. I guess you don't need the plus c there because we can leave that because we didn't integrate yet.
So it cancels out the d.
Yeah.
Not the y.
Yep, just the derivative or differential in this case.
So why wouldn't it do it to the left side too? Or is it just because the differential is just focused on function?
Yep, because right now we're differentiating with respect to x.
Okay. I gotcha.
All right, now we can go to the actual formulas, which the formulas are kind of just the reverse of what you've been using already. So if you know your derivative formulas, you kind of already know your differential your antiderivative formulas. Okay, so called antiderivative of f or integral, indefinite integral. We'll do definite integrals later.